You can prune away its branches, even cut the tree to the ground, but it will grow again, ever stronger.
Hello, welcome to another episode of The Emperor's Armory. Welcome to the channel. If you haven't subscribed, then please do. So, yes, as the intro said, this video, as the title says, this video is about trees. Trees of doom, evil trees, oh my goodness. And unfortunately it's not a particularly exciting set of trees. It's actually going to be a bit of a slow, kind of boring, kind of technical video. So if you're interested in a technical deep dive on data structures and optimization of data structures, then this is a video for you. Stick around, and if not, well, stick around anyways, or at least like and subscribe, and there should be more exciting stuff in the future. But anyway, okay, so this one is about a type of data structure known as a quad tree. And so what I'll first do is I'll explain what the problem is. And the problem is in the context of building an RTS game, and how can you optimize the performance of the RTS and the data structure, because an RTS has a lot of moving parts, and so you have to have optimized ways of handling those moving parts, of running those calculations, because if you don't optimize, then the whole thing will grind to a halt and you won't really have a high performance RTS. So what I'm going to go into is a quad tree, and how we are going to implement it in our game, The Great War, built by the Emperor's Armory team and myself. And so, okay, I'll jump into it. First I'll explain what the problem is, and then I'll explain the solution. There's about 3 layers to the solution, and it's a lot of stuff, but we'll get through it. Okay, so first of all, let's describe what the problem is. So this grid here represents a 2D data structure, just a standard data structure. Let's say, for example, it's an array of arrays, or a vector of vectors, or a list of lists. Kind of doesn't matter. Don't worry about what language, it just is a 2D data structure. And this represents the grid of the map in the game. So it won't be displayed like this, it will be displayed isometric, but mathematically, when you're running the calculations, this is a good representation. And in this grid, we've got objects. So here is an object here, and an object over here, and another one over here, etc. You have all these objects throughout the map. So here's what the problem is. Let's take this arrow as a pointer. So as you're going through the 2D array, you iterate over them. So here's the first, and the second, and the third, blah 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 blah. So when you want to interact with the first object in this 2D array, how many steps does it take? 1. It takes 1 step. Okay. How many steps does it take to get to this last one over here? Well, 1, 2, 3, 4, 5, 6, blah 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 blah. 36. Takes 36 steps to get to something over here. So in the case of where we've only got these objects, well, okay, let me rephrase that. When in the case of where we've got 2 objects which are right next to each other, we only have to iterate through 2 times. 1, 2. Well, I think it'd actually be 3. It'd be 1 and then 1, 2. So there'd be 3 iterations. But let's, instead of saying that there are 2 objects over here, that there are in fact that there are in fact 2 objects over here. Well, then that's not 3 iterations. That's like 36 iterations and 35 iterations. So that's over 70 iterations to simply just interact with this object and this object and get them to do something together, or to get them to do something with this object back here. So this is really super inefficient. If we use this type of data structure, the game would just grind to a halt. Like, you wouldn't be able to have more than just a few objects before the performance would tank. So this is a conventional 2D array. So how we can solve it is this. This is a quad tree. So like before, here we have an object in this quad, or this location up here, and another one up here. So let's now count how many you have to go through. So remember, up here it was 36 or 35 steps to get to here. Let's count this one. So okay, here is 1, okay. Now let's count to the bottom one, to this one over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That was 12 steps. So how did that work? Because there are more than 12 cells in this particular grid. Well, here's how it works. Because this cell is empty and these ones are empty, we don't have to go further into these quadrants. I think actually I've got that slightly wrong because yeah, I have got that slightly wrong. We would have to iterate through these ones. But certainly when we come to this one, this is empty. So you just count the whole thing as 1. This whole thing is 1. And then this would be 1, 1, 1, 1, 1, 1, 1, 1. So that wouldn't be 12. In fact, it would be 1. Well, I'm not going to count it through, but it would be a whole lot less than the 36 that was up here for sure. So, okay, that's great. So then what happens now if, let's say, we've got 2 objects down here, and we still have to count them, we still have to find where they are, and then go to them and run a calculation, etc. So how many steps would we get for these two? Bearing in mind, up here was something like 70, just between just 2 objects over here. That was 70. So here we have to go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16, so that's half the number that this one took. And then again, this would also be like half the number that this one took. So rather than taking like rather than taking over 70 steps, this now is like around 30 steps, probably a bit more than 30. But it just shows how, with changing the structure, with rather than having every single line drawn into the grid, that by cutting out lines and cells where there are no objects to deal with, we can drastically increase the speed or the number of calculations that we can make to interact with objects inside the data structure. And this is called a quad tree, and it's quads because these are all quadrants, and a tree because they have branches. So you can see this one here, well actually the first area is the outside square, and then the second area is this one here. This is the first quadrant. Well, this is actually the first quadrant. And then you can see the first quadrant is subdivided into more quadrants or branches, and then each of them, or this one, has additional layers of branches. So this is the highest resolution set of quadrants, and then medium resolution, low resolution. Okay, so that's how we can optimize iterating through objects. So how does that relate exactly to our game? Because it's not just about maths, we're actually trying to produce actually a playable video game. Well, okay, here we go. Here is an object, and it is in the the highest resolution of quadrants in our data structure. And this here represents the player's camera. So as the player is going around the map, here's what they can see, and here's the view. So whatever is inside this area is what the player can see, whatever is outside of this area is what the player cannot see. So the player is over here, and there's nothing over here, so there is nothing rendered to the player's view. However, when the player is over here, bearing in mind that this is actually just like a isometric three-dimensional, pseudo three-dimensional representation of this. So even though so this here is actually this here, even though there's nothing in it. In fact, I could draw that there and there and it would be the same, but I'll not bother. But so when the player is here, then all of a sudden there is something in this quadrant, and so this does get rendered. Okay, well, that actually doesn't really matter, because it wasn't going to get rendered anyway, because there was nothing in this quadrant and nothing in this quadrant, so there was nothing going to be rendered regardless. But what changes is that our game doesn't have simply one tier of map. Our game actually has multiple tiers of maps, multiple scales of maps. And this highest level scale, the lowest resolution, this low resolution map represents the strategic map. So let's say, for example, that London is like here, Berlin is like here, and here's like a front line of British and a front line of Germans. And let's say that you're on this one up here and you're viewing, and you can jump between London and you can jump between the front line. You can switch to London and the front line. Or if you're playing Germany, you can go Berlin and the front line, Berlin and the front line, or whichever factions you are and whichever front you're fighting in. And you're all inside the strategic map. And the strategic map can cover entire countries, entire continents. You can take the mouse and you can move the mouse left and right, and you'll be able to move across huge swaths of land and see entire nations just by moving around your mouse. And that's good for controlling economic units or going to a city and whatever, that's good for that. But when you want to actually control a unit and get in and fight and control unit by unit, move infantrymen or move cavalry or fighter aircraft or whatever, well then this view up here, this low resolution view is no good. You wouldn't even see infantry or horses or aircraft on a map of this scale in real life if it was like a satellite image. You wouldn't see it at low resolution. So then you use the mouse wheel and you scroll in. Now you're in the tactical map. And in the tactical map, now you can see infantry and you can see aircraft and horses and trenches and machine guns and all the rest of it in this view in here. And so the trick is that while you can see that stuff, the two maps are actually connected. So let's say that in here, this area is particularly hilly. Over here, it's high resolution hills and mountains, and here you are fighting in this area. Well, when you scroll up to the next highest map level, what you'll see is that in this region there are mountains. There'll be a low resolution mountain, and it will be bigger. So here are like smaller resolution mountains, there's more of them, they're smaller, but you see them in finer detail because it's higher resolution. But when you scroll up using the mouse wheel up to the higher strategic level, you can still see indeed that there are mountains in that location. There are fewer of them and they're much lower detail, but it does represent the two maps are connected to each other. So there's that nice connection between the two of them. So again, we can handle this with the quad tree because here's a bit of a catch. So in this quad tree section over here, we can see that there is nothing inside this quad tree, and so there is nothing drawn to it. But actually, in our game, because we're going to draw a map, everything in the map has a cell, everything has a quadrant, so we can't actually leave blank spaces like this. But just because everything has a map, it doesn't mean everything has to be of the same resolution. So as you can see over here, yeah, sure, this quadrant doesn't have anything in it. Oh, let's just say, let's say here are the mountains, and they're over here as well. Okay, so this quadrant does have mountains in it, but this quadrant does not have mountains in it. That means that although every single thing has something in it, it doesn't all have to be the same resolution. Some of them will have to have like really like high resolution things going on inside of it, but some areas can just have like low resolution things inside the map because not every section of the map has the same amount of stuff going on in it. So okay, this is just a general high level overview of how the quad tree will help us to draw the map and handle what the player views as they're going through the map. Oops. Try that again. Yeah. What's with this? Sorry about that. Try again. Yeah, there we go. Okay, so as the player is going through one scale of map and then zooms down to another scale of map, the quad tree will help us to change the amount to manage the resolution of data that is being drawn. So although the map indeed will have the highest resolution all the way through the map. Because it's stored as a quad tree, we don't have to display all of the resolution at exactly the same detail, and so we'll be able to cull huge amounts of resolution just purely based on the player's view and where the player is inside the quad tree. And if they're not inside that quad tree, we can greatly reduce the resolution that has to be displayed to the player at any one moment. Just cut it. If it's not inside the view, just cut it out, don't display it. Okay, so again, high level overview. Now here's an additional layer of problem solving, or of optimization I should say. So up to this point I've kept saying that here is the object. So like here is the object, like up here, or on this one over here, here are the objects. I'm going to now change what I mean by the term object. So in this one, the object might literally be a tank, or a mountain, or a sprite that you're drawing, or an artillery shell that's flying across the battlefield, or a trench line, or whatever. It would be like an object in the sense of like just plain English object. It means a thing. Now let's change what the word object means, and this is now no longer an object. Instead what this is a pointer. And this is now actually going into C++. We're not just talking agnostically about language concepts or programming concepts, but we're now speaking explicitly about a C++ pointer. So here is the pointer, and the pointer is pointing to an object in the sense of programming, computer science object. So what does a pointer do? Well, a pointer is a bit like an address. If this is the address, then this is effectively like the house, and this list over here is effectively like the street. So all the houses on the street, they don't move around, they are where they are, they don't move. But the address, maybe it's just a piece of paper, and you can carry that piece of paper around in your pocket. It's very lightweight, and if you move the piece of paper around, like let's say, just for the sake of the analogy, let's just say that this was one pocket and that this is another, that this is another pocket. You can move from one pocket to the other with a piece of paper. That's really super easy to do. But it's not super easy to move an entire house from one pocket to another. And it just isn't possible to do that. So by using pointers inside the quad tree and pointing at stationary objects inside a list, we can greatly optimize the performance of the quad tree. When we have to go from, when we're iterating through the quad tree, like here, rather than having to iterate through an entire object and go through every part of the object and look at everything that the object is made of and go, oh no, that's not the right one, let's move to the next one. That's super slow. But in this context, it's not an entire object, it's just a pointer, and we can quite rapidly move through pointers and then go in, and if it is the correct pointer that we're looking for, then we can go directly to the object, and if it's not the correct pointer, then we can quickly just iterate onto the next one far more quickly than if we're having to iterate through objects. And then also an additional thing about the pointer is that the pointer will have a position, and so when we want to go backwards, when we're doing something with the object, like let's say that this object here, that this object is, say, an enemy unit, or these are two opposing units and they're attacking each other, but let's say like this object is object 15, and this pointer is pointing at object 0, let's say, the first one, the 0th index. We can quickly go back onto the map. We can quickly draw, or we can quickly interact with the map without having to move the objects around, and without having to wonder where they are inside the quad tree, because the address inside the quad tree is stored in the list. So object 15 currently is in position 15, but object 15 might say move to attack object 0, and when it attacks object 0, and let's say object 15 wins, let's say these are a bunch of soldiers and they fight and they win over here, we don't have to change the position of the object inside the list. Instead, we just update the position. It's now at 1414 rather than 1515. And by doing it this way, we can jump very quickly to the exact location inside the quad tree without having to iterate through, oh, where was object 15 again? 1, 2, 3, blah, blah, blah. No, you don't have to do that. Instead, you can just look at this address and then jump immediately to position 1414 or 1515 inside the quad tree. So yeah, it's to be honest, like, if I sound like I kind of don't know what I'm talking about, it's because partially I don't. Like, I haven't actually tried to build this yet. I'm still pretty new to quad trees, and it's me just kind of like figuring out ways to optimize ways of problem solving objects interacting with each other, but not just like 1 or 2 objects, because you could just brute force 1 or 2 objects, but we have to figure out ways of optimizing for thousands of objects and at different scales, and have a way that makes it feel like all of those objects are interacting all at the same time. So that although maybe actually we'll have to figure out additional ways of optimizing direct interactions, from the player's perspective, they don't need to know that not all of the calculations are being done. It's just irrelevant for their playing experience. So later on we'll find ways of optimizing actual interactions. But this quad tree, and particularly the quad tree in combination with pointers being stored inside the quad tree, and then those pointers pointing to a list of objects, and the objects inside the list remaining stationary and having an address to point back at the quad tree, this should give us a huge leg up. Time will tell if this is the only optimization that we need. Probably not. We'll probably need to figure out something else. But certainly this is a great place to start, I believe. I've looked at a couple of other data structures and done a bit of research about it, and it seems like this is a great way to do it. So there's the technical video, the geeky deep dive into evil trees of heresy. It's a difficult thing to do, but that's what software engineering is about. It's about taking on difficult challenges and solving them, and looking for ways to optimize so that you can really get the sort of performance that you're looking at. And so this is what it's all about. Anyway, so thank you very much for watching this video. If you did, if you're not subscribed, please subscribe for more. We're still in the very early stages of building our game, the Great War, on RTS about World War I. So we don't have too many exciting things to show at the minute. It's still kind of like really down in the bilges, working out the guts and the gears of the project, and building an early working prototype. So this video is maybe not super exciting, but if you're a technical person and you're interested about these things, then you should have found it interesting. So again, thank you for watching the channel. Like, share, subscribe, all that stuff, and I'll see you in the next one. Thank you very much. Bye-bye.